So here's the last topic I want to discuss um, as a final little topic, just to cover all the bases. It's called the binomial series. And it's called binomial because you're taking a binomial and you're raising it to a certain power. There's something called the binomial theorem, which is really what this stems from. It's when you have a binomial. So if you recall binomial theorem, you have something where you have a binomial raised to a power. And usually we're considering n to be some positive integer. And the theorem states that you go from I from 0 to n, and then you have this n choose I business, x to the I, and then y, or I should say a to the I, b to the n minus I. So this is something, if you don't know it or haven't seen it, that's okay. But if you have, it's just a refresher. It's the binomial theorem. This is just a way to write a shorthand notation. Always the summation is to write things in shorthand. Normally, when you have a binomial and you raise it to the second power, raise it to the third power, you have this kind of usually go the other way. It doesn't matter. It's just usually it's just the exponents of a and b. They're just numbers that as you start to see I goes from 0 to n, so these exponents decrease by 1, and then these exponents for b increases. And we've seen this before. I'm not going to dwell into this, but we've seen things like this before, to the first power, and then we're using binomial coefficients, n choose 1 plus n choose 2, a to the n minus 2b squared, all the way back down to b sub n. This is in its generality what the binomial theorem states. But now we're considering a binomial series, particularly when one of the values is 1 and the other value is a variable x. And instead of assuming that the exponent is a positive integer, we're assuming that k is any real number. So that's really the powerful key aspect behind the binomial series. And this looks very similar to the binomial theorem. As you can tell, my a value 1, if I raise 1 to any power, it goes away. It becomes just 1. And I'm left with just the x variable being raised to the n, and n goes from 0 to infinity. So what it's going to look like? It's going to look like when n is 0. And again, all of these different series just stems from using the procedure to find a Taylor series. So if I had to actually find the Taylor series behind this would be my f of x. Then I would find f prime of x, and so forth, f double prime of x, and then continue on and so forth. And these are the coefficients I get. These are my coefficients. And these coefficients can be represented by a binomial coefficient representation, which looks like this. So all of this is just a means to an end. It's a means to explain, or to explain the series representation of a binomial expression such as this. Okay, so even if this doesn't make the cleanest sense in the world, you can always find it by applying the procedure for finding the Taylor series, which is finding the derivatives. But if you just don't want to pursue that route, you can use this little shortcut. So think of this as just a shortcut. Okay, let's look at an example of a binomial series, which we've seen already. Let's see, when we have something like this, 1 minus x squared, remember, we consider this as the derivative of 1 over 1 minus x. That's what the derivative is. And then we saw that this is the derivative of the power series representation of x to the n. And when we take the derivative of every term, term by term, n equals 0 to infinity, we take the derivative of x to the n. Again, I'm just reiterating this because we've seen this a lot. And this is the integral of nx to the n minus 1. And n starts from 1 to infinity. The reason why we start from 1 is because originally that x to the 0th power is just a 1, and the derivative of 1 is 0. So that 0th term is no longer there. So I don't have to write that anymore. So I can start from 1. And if I write out the series, it starts as saying I have a 1 plus an x, right, plus an x, and then plus a 2. Let me just say it's 1. When n equals 1, I get 0. And then when n equals 2, pardon me, this is a 2x. And then this is a 3x squared, and so on. So we've seen this before. We've calculated the power series representation, which is this one here. And this is just the expanded form of the power series. And it's a Maclaurin series, particularly because it's centered around 0. So we've seen this already, and I've also computed this using the procedural way of finding the Taylor series. Now I want to find the same series just using this idea of the binomial series representation. So what I have to do here is I can represent this as 1 minus x to the negative 2 power. Now, according to the binomial series here, I just use this notation. What's my k value here? My k value is negative 2. And then if you study this a bit, I have a plus x here, but in this case, I have a minus x. So that means that I'm going to replace the k with the negative 2 n, right? This is a binomial coefficient again. And I'm going to write this as negative 1 to the nth power times x to the nth power. N goes from 0 to infinity. Okay, and so then this equals, just want to make sure, this equals, according to this formula as well, I got a 1. That's the first term I get. Then I get a k. My k value is negative 2. And according to this formula, I got a negative 2, and then I have a negative 1 because this is n equals 0. So n equals 1, I got a negative 1. And I got x to the first power. And then the next term, right? The next term is negative 2, negative 3 over 2 factorial. I got a negative 1 to the second power times x to the second power. Right, that's n equals 2. Then n equals 3, I got a negative 2, negative 3, negative 4 over 3 factorial, negative 1 to the third, x to the third. And of course, this continues, dot, dot, dot. But let me just clean this up a bit. This becomes negative times a negative is a positive 2x. Negative times a negative is a positive times a positive. So I have a positive. And the 2's cancel here, and I'm left with a positive 3x squared. Then the 3 and the 2 cancel. And the negative times a negative is a positive, times a negative is a negative, times a negative is a positive. So I get 4x cubed, and so on and so forth. But guess what I just wrote? I can rewrite this as the series where n times x to the n minus 1. You notice the exponents are always 1 less than the coefficients. I write my exponent, my coefficient, as greater than, or I should say my exponent 1 less than the coefficient, and my coefficient can start at, my n's can start from 1 to infinity. So I was able to get the same representation as I got originally, either by using differentiation or by using the procedural method of finding a Taylor series, I can just get that quickly, a little bit more efficiently by using this binomial series idea.